thank everyone for joining us today, and welcome to the National Urban Research and Extension Center's webinar on agroecological functions of soils in the city. This is by NUREC's inaugural sabbatical fellow, Dr. Doug Collins from Washington State University. Before I turn it over to Doug, I'll just give a little bit of information about the National Urban Center. You may have known us before as the Western Center for Metropolitan Extension and Research. We are currently rebranding ourselves to better represent our national footprint as a collaborative, membership-based, nationwide organization for land-grant universities that facilitates the co-creation and application of knowledge, enabling metropolitan communities to improve the health and well-being of all residents, achieve equitable economic growth, and steward their natural environments, delivering on the land-grant mission for urban residents, communities, and the organizations that support them. Now is a good time to join us if you're interested. We are an organizational-based membership, so you join as an organization and you can see the 14 land-grant universities that are members. Our fiscal year starts July 1, and some of the things we do is funding fellows that we have, deep dive fellows, sabbatical fellows, and graduate student fellowships that we offer. You can also join our listserv. It's the link is down there at the bottom at lists.wsu.edu/mailman/listinfo/NUREC. Or you can send me an email and I can send you the link for that. Also invite you to join us at the National Urban Extension Conference that's coming up in May, where several of our fellows will be presenting. So we'll have a grad student fellow presenting on the effects of urbanization on peri-urban agricultural soils in the Puget Sound, another grad fellow on the role of extension to enhance urban tree planting programs, and that's from the Portland area, a panel of deep dive fellows who have been working on addressing professional development and progress for urban extension professionals, and they'll look at that from an ecosystem perspective. And then also a grad fellow of exploring the human side of urban agriculture. And unfortunately, some of these do overlap, so if you want to attend them all, you may need to be like a planaria and divide yourself prior to the conference. With that, I will introduce Doug here and then turn it over to him. Dr. Doug Collins is an extension professor and soil scientist with Washington State University's Center for Sustaining Agriculture and Natural Resources. He's located at the Puyallup Research and Extension Center, which is part of the metropolitan area of Seattle and Tacoma. He has a PhD in soil science from Washington State University and a master's in plant pathology from Montana State University. And with that, I will stop sharing screen and turn it over to Doug. If we have questions, I would prefer you try to use the Q&A and then I can monitor them for you, Doug, or you can, depending on where we're at and people, you can raise your hand and just come off mute and ask questions.
Okay, hold on, I'm not sure I shared that right. Thanks, Brad. There we go, let's share that one. Does that look good?
There we go. Yep, that looks great. Thanks.
Oh, I don't see the. Okay. Well, thank you, Brad, for that introduction, and thank you, everybody. Good morning, good afternoon. It's a pleasure to share some of my project with you and hopefully hear some good discussion. So I will jump right into it. Today I'll give a brief introduction to anthropogenic soils and urban agriculture, and then provide some results from the National Urban Research and Extension Fellowship that I was awarded. And this was also combined with a sabbatical from Washington State University. And so during that part, I'll talk about the project that I undertook on my sabbatical, methods, results, and some reflections, and then also a little more reflection just about the opportunity to have a sabbatical and dive into something a little bit different. I will say in my work, I work primarily, I guess, with small scale farms. A lot of peri-urban agriculture has really been where my focus has been. And up until this project, had not really delved into urban soils or anthropogenic soils. So this was related to my work, but an opportunity to dive into something a little bit tangential. Some soil science up front. So petagenesis is the natural process through which soil forming factors interact to form a particular soil. Once soils are formed, you can look at the different horizons of a soil. And, we see the topsoil, we call the A horizon, and the B horizon, and then the parent material is the soil that the material that the soil is forming on. And so petagenesis is this natural process that leads to these distinct soils or also soil series, and we can describe the processes that occurred by examining those different horizons and the physicochemical properties of them. Anthropogenic soils or anthrosoils are soils that have been influenced, modified, or created by human activity, in contrast to natural processes. And anthropogenic soils can come about in 3 different ways: sealing, transformation, or transport. And so this shows a way that sealing could lead. Basically, pavement was put down, that natural pedogenic process has been interrupted. I didn't take this picture, but I love this picture because you can see how there's soil below here, and then there's soil probably coming on top of the ceiling as well, and you can see that the life within that soil is basically fighting its way through that ceiling. So one way to create an anthropogenic soil would be to seal it, and then maybe that material is removed, and then petagenesis continues again in a more natural way. So transformation is something we see a lot, and I'll talk in a few slides about what is just sort of the agricultural impact on anthropogenic soils. So agriculture basically is transforming. There's a lot of different ways to transform soils in through human activity. Tilling, irrigation, adding amendments. And then finally, transport. So this is a farm in Chicago, and all of the soil at this farm was transported to this site. And basically the soil formation that's happening is happening on this transported material at this new site. This process of petagenesis or soil formation has been described through what we call soil forming factors. So Hans Jenny in 1941 came up with the 5 soil forming factors. This idea that a soil that we find in any particular place is a function of 5 soil forming factors. We use the acronym CLORP to try to remember those. So climate, organisms, relief, parent material, and time. So any soil in any particular place is can be described by how these particular 5 soil forming factors come together. And so, for example, you can find soils that are very similar, in eastern Mongolia in eastern Montana, that you would find in Mongolia, because the climate, the parent material, everything kind of came together, even though they're not very close geographically. You can find that if these 5 soil forming factors come together, you can find similar soils in disparate places. In the case of anthropogenic soils, one or more of these factors may be altered by human activities, and human influence can be incorporated into this factor approach in 2 ways. The first is that humans are just an organism, and that the impact that humans have, we just kind of put that in the organism category, and we consider that, we just still consider those 5 soil forming factors. Another way to view this is the anthropogenic factor, so adding an A to that original 5. And the argument for considering humans as a separate factor is, unlike other organisms, humans are purposeful manipulators of soil, and also human effects on soil occur on different spatiotemporal scales than those of other organisms. So for example, the earthworm pictured here, in terms of soil ecology, we call earthworms ecosystem engineers, and they're very unique. You know, they have this functional role in soils that's unique compared to bacteria or fungi, you know, the decomposers or the shredders. The ecosystem engineers, we also put ants and termites in that category. They physically move soil. They change the soil habitat. In earthworms' case, they're changing it oftentimes to suit their own physiology. And so that's, you know, magnificent, but I think arguably humans are still operating in terms of this on different scales. So this table just shows how humans can affect all of these different original soil forming factors, climate, in terms of, you know, just adding irrigation. We're changing the water structure of a soil or the water dynamics that can have huge impacts on what grows there. Global warming and climate change, it's arguable that it's hard to find a soil that hasn't been impacted by human activity, since the entire climate has been impacted by human activity. The next slide, I'll show how land formation can be changed by human activity, and even in a large agricultural setting. And then let's see, for example, with organisms, the introduction of invasive species, parent material. Humans are, you know, when through agriculture cause a lot of erosion that can create basically the loss of that topsoil, and then you're exposing, you know, new material and sort of changing the soil forming, like the processes, maybe even completely exposing new parent material. And time, resetting soil formation clock to zero through disturbance or excavation. And then this can happen, you know, I think in terms of urban agriculture, you know, it's sort of obvious that oftentimes agriculture or production is happening on highly disturbed areas. But even in this is a coffee plantation in a, you know, rural area in Hawaii, and I was struck by how much soil movement was done purposefully before planting this plantation, in order to sort of create, you know, the right water dynamics that they wanted for this particular area. So it can happen on large farms as well as smaller scale. When we study soil forming factors, one beneficial way to sort of isolate the effect of one factor is to do a gradient study. And one classic gradient study is called a chronosequence. So if you look at the, this is so isolating the time factor. So if you look at the Hawaiian Islands, Kauai, the oldest island, is 5.1 million years old. And the island of Hawaii, the big island on the south end, was sort of birthed 0.7 million years ago and is continuing, you know, to create new parent material up to this point. So all for most purposes, you know, all the other soil forming factors remain constant, but the difference is time. So we can study soil development on these islands, and basically, you know, as long as you're on the same side of a hill on a particular island, the same relief you control for that, you can isolate that time factor and study how time affects soil formation. Another example, this is from Washington State, would be a climosequence. The Palouse is in eastern Washington, or Pullman is in eastern Washington over here, and we call this area the Palouse, but the parent material is similar for this whole area. but the climate is very different. We have the Cascade Mountains here, and just on the eastern side, there's a rain shadow, so very dry in this area. And then as we get closer to the Rocky Mountains, we start to get more sort of a second orographic effect, and we find more precipitation as we get closer to the Rocky Mountains. So there's a nice climo sequence that can be pictured in the Palouse. In studying urban soils, you can create an anthroposequence, which is used to evaluate the anthropogenic factor. So for example, this is Tacoma, Washington, but you're looking at a city center, very disturbed, highly influenced by human activity, and then moving out to less disturbed, more natural soil forming processes. So that would be called an anthroposequence. The term metapetagenesis has been used to distinguish soil formation on human disturbed soil from natural petagenic processes. So, quote, natural soils are not directly influenced by human activity, whereas metagenic soils are natural soils altered by human activity, such as agriculture. Missing words here. Oh, and neogenic soils are soils formed on transported material. So, for example, that thinking back to those other terms, the sealing, transport, and transformation. So the metagenic would be transformation, and then the neogenic would be transported material. So soil forming on fill dirt, and with the neogenic, you can have an in-ground neogenic soil or an isolatic neogenic soil, which would be soil that's isolated from the surrounding environment in a container. More taxonomy for soil nerds. To be classified using the anthropogenic soil profile, a surface layer of human transported material or human altered material greater than 50 centimeters must be present. Most anthropogenic soils are classified as intsols, and human altered material can be deep plowing, excavation, or surface compaction. Some of the we call it things you might see as you're digging a soil profile. We would call those diagnostic characteristics. And so the first is just the human altered material. So here we have a farm outside of Chicago, for all, basically a natural, been in farmland as long as, for centuries probably. Hasn't been disturbed by urban development, but has been altered through agriculture, probably some deep plowing, some addition of materials. Human transported material. So these are the containers, so that kind of isolatic environment where the parent material was transported and moved to a new location. Artifacts are something, a diagnostic anthropogenic characteristic that we would document when studying an urban soil. So here, at the surface, it looks fairly normal. Digging down and even through the top A horizon, rich in organic matter. And then as we get below that, we find bricks, the remnants of a previous foundation or a wall or something like that. So that's sort of underlaying the current topsoil. Another common diagnostic characteristic of an anthropogenic soil would be a manufactured layer. In Chicago, these types of farms are common. They're called cap and fill. So due to some contamination, some desire to isolate the above soil from the below soil, a manufactured layer is placed over that original soil, and then new soil is brought in. In terms of where one is in the city and what they find, the structure of the cities matter, and there are some different city structure models that have been developed. Most North American cities fall into this concentric zone model, where we find the central business district, that's what the CBD is, and then the central business district tends to be where historically there was a lot of industrial activity. At present, it's probably more poor, and then as you get out into the suburbs, distance away from the central business district, we see increasing income. There's the sector development following major rail lines. So development might have occurred, along those different rail lines. It can be a little more sparse. Multiple nuclei method, where there's multiple small cities kind of around maybe one larger central business district. The urban realms model, this has been used to classify, for example, San Francisco and Los Angeles. A lot of European cities have this sort of prevailing wind direction, so there's increasing income in nicer areas, sort of like upwind of the central business district, compared to the maybe poorer areas downwind of the central business district. And then in Latin American cities, it's a little bit different, where almost kind of the opposite of the North American cities model, where there's something that sort of ties the city together in the central business district, maybe a zocalo, and then poorer areas end up on the outskirts of town as we kind of move away from the central business district, the periférico or barrio, kind of the poorer neighborhoods. So depending on how a city was formed will affect perhaps what the urban soils look like. So urban agriculture is an important ecosystem service that we can get from urban soils. Food supply is obviously an important service that can come from these urban ecosystems. The global population living in urban areas is increasing, and this trend is set to continue, with about 70% of the global population estimated to inhabit urban ecosystems by the year 2050. Supplying food to cities is a key contributor to greenhouse gas emissions, biodiversity loss, water pollution, land use change, non-renewable resource exhaustion, and other pressing global environmental challenges. Globally, about 800 million people may be engaged actively in urban agriculture practices. 266 million households engaged in urban crop production in developing countries. And this takes place in allotments for self-consumption, large-scale commercial farms, community gardens, and edible landscapes. And urban agriculture can occur on many different scales, from rooftop gardens to larger cultivated open spaces. One statistic cites that only a third of the global urban area would be required to meet the global vegetable consumption of urban dwellers, but there's only limited potential to contribute to global cereal production. Some other benefits of urban agriculture: reduced food transportation distances, carbon sequestration, reducing the urban heat island effect, improved aesthetics, community building, employment opportunities, improving local land prices, shortened supply chains, provision for habitat for wildlife, waste recycling, and improved physical and mental health, supporting numerous health benefits. So I think this is really important to keep in mind. Can urban agriculture completely disrupt our food supply chains? I'm not sure, but I think it can have an important effect on food supply. But there's also all these other benefits to urban agriculture that I think that should be valued and encouraged. It's not all roses, of course. Contamination of urban soils with trace metals and organic compounds can restrict their use for urban agriculture. A few things to note here. If contaminants are present, their availability can be moderated. So for example, by altering the pH affects the availability of some compounds and can be stabilized in situ with liming. So for example, copper, zinc, lead, and mercury, their availability can be reduced by increasing pH. And the largest risk to human well, so first of all, infants are certainly at the greatest risk, and the inhalation of or ingestion of dust contaminated with heavy metals is probably the most concerning method for, or the most concerning route of exposure for soils. And one study found that the most significant factors related to elevated lead levels in children were the age of housing, road density, and percent impervious surfaces, which is probably linked to increased lead-rich dust within a home. Crop, the idea that crop up, like getting lead exposure through crops grown in lead contaminated soils, that can happen, but direct ingestion is definitely the greater concern. So low growing leafy vegetables or root vegetables can accumulate lead in their core, and but primarily it's that soil ingestion that really has to be taken into account. This is a great article that just came out, The Legacy of Lead in City Soils. I think this is available free to anybody. The CSA is the Crop, Soils, and Agronomy News. And so I would encourage you to check that out if you would like to learn more about what some new research and direction on lead in soils. Some of the findings from that, or the highlights in that study, they looked at, for example, one study looked at parks and really trying to tie the past industrial landscape to those parks, and even within a certain park, they found localized hotspots. So the past contamination of lead can be quite local. Other sources of lead were obviously like leaded gasoline, are a little bit more widespread. But also getting a sense of kind of like what are background levels of lead, and then what are concerning levels. And I will note also that just in January 2024, the EPA lowered what's called the screening level, or the threshold level for lead, from 400 parts per million to 200. So it is definitely something that to be aware of, and I think in terms of it's a different level, or a different, when we talk about soil health or soil quality in a peri-urban or a natural environment, that contamination history is not like the most important thing probably on our mind, but in an urban setting, I think it really needs to be. We need to start there. We need to understand the levels of contamination, and then also try to be realistic, I think, about what the risks are in terms of using it for agriculture. Okay, so moving on to my particular project. I did an observational study of soils in 3 different agroecosystems in 3 metropolitan areas, Medellin, Colombia, Chicago, Illinois, and then the Seattle, Tacoma area. So for my study, I came up with 3 different soil types, a peri-urban soil group, which was thought to be kind of a control. So, soil that has obviously been influenced by humans, but in that more metagenic sense, where we didn't transport a lot of soil, there hasn't been sealing, but there has been, tillage and just kind of the agriculture that we normally think of, or the disturbance we normally think of associated with agriculture. The second type was an urban in-ground soil. So this would be called a neogenic soil, highly disturbed, maybe on transported material, but in ground. And then also looking at that neogenic isolatic soil, an urban container. transported material in rooftops or pots. There was a third one that I did not have on my original plan, which was this cap and fill type of farm. And this I only did in Chicago because it seemed like every farm, a lot of farms fit this model in Chicago. I wasn't able, I did eventually find the soils that I was looking for in this urban in-ground category in Chicago, but there were many more of this urban cap and fill. And that seemed to me to be sort of like between isolatic and neogenic in terms of the way I was thinking about it. So I sampled three, or I added that category, but only in Chicago. So just a little background on these areas. Medellin is the second largest city in Colombia with an estimated population of 2.5 million, and the larger metro area has more than 4 million people. It was identified in February 2013 by the Urban Land Institute as the most innovative city in the world due to advances in politics, education, and social development. It has a large public transportation system that includes train, metro cables, and outdoor escalators. It's at 4,900 feet, 1,500 meters, and has an average annual temperature of 22 degrees centigrade or 72 degrees Fahrenheit. And it's known as the city of eternal spring. So this was a highly desirable place for, these are my two boys, so we took our whole family to Medellin and spent 9 weeks there, riding the metro cables, finding urban farms and peri-urban farms, and really enjoying the culture of the city of eternal spring. Chicago is the third largest city in the US with a population of 2.7 million. Chicagoland, or the Chicago metropolitan area, has a population of 9.6 million. It's of course known as the Windy City. It has an average mean temperature of 52 degrees Fahrenheit or 11 degrees centigrade. And Seattle and Tacoma, population of 750,000. It's the 15th largest city in the US. The greater metropolitan area is about 4 million. Seattle's called the Emerald City with an average mean temperature of 53 degrees Fahrenheit and 12 degrees centigrade. And I spread my study out from Seattle to Tacoma, which would be considered this greater Seattle area. And I am currently right here in Puyallup. And each site was geolocated and described through a soil profile description, including structure, texture, bulk density, and total carbon analysis at 0 to 15 centimeters, 15 to 30 centimeters, and 30 to 60 centimeters, with the exception of the container soils, which were only sampled at 0 to 15 centimeters. Surface soils were further characterized for soil nematode community analysis, soil nutrients, and mineralizable carbon, as well as soil arsenic and lead. This is me smuggling my soil samples from Chicago back to Seattle. So when I was in Medellin, I worked with the Universidad de Antioquia and did all of the nematode analyses there. I did send soils through the mail to a lab that was able to receive soils internationally, but that was just for the analysis of the fertility and sort of the chemical parameters. So I did the biological work in a lab in Medellin. In Chicago, I did more of that work back in Seattle, so I brought those soils home, and TSA did not like to. They actually, I had 27 bags in a larger bag. They took each one and tested it for explosive residue individually while I was hoping to catch my plane back to Seattle. It all worked out. In terms of analysis, just sort of a general observation of the range of soil parameters relative to standard recommendations. I did analysis of variance with city and soil type as factors. One caveat of that, applying analysis of variance to an observational study, it is helpful in terms of within this data set to isolate where there are significant factors, but because it's an observational study and not a design study, it's there's less confidence in applying those results, to a new data set. And then also I use multiple linear regression to model mineralizable carbon. And I think that's interesting. I'll show the data related to that and hopefully explain what that means. But I will also say I did try multiple linear regression on several other parameters and unable to find a model that fit those. And I think that's equally important and also a good lesson from these data. And that comes out to you in terms of looking at the correlation between parameters. So parameters that had a significant farm type effect, those are listed here, and I'll go through and show some dot plots of most of these. And so again, that would be, is it a peri-urban farm? Peri-urban, the urban in-ground, or the container. And then parameters that had a significant city effect are listed here, and that would be Medellin, Chicago, or the Seattle-Tacoma area. And parameters not significantly affected by farm type or city, mineralizable carbon, carbon to nitrogen ratio, potassium, arsenic, silt, clay, and then the nematode indices, the enrichment index, structure index, or channel index. So I won't talk too much about that in this presentation, but what we're doing with nematode analysis is looking at the different families of nematodes that are present there. Some families are related, for example, to lots of nutrient inputs, so there would be a lot of bacterial feeding nematodes. Some nematodes are related to nice stable environments, and that increases what we call the structure index. And then the channel index is an index of fungal feeding nematodes to bacterial feeding nematodes. All right, so as I mentioned, organic matter was significant for farm type. So the container soils had the highest organic matter, followed by the urban in-ground soils, and the lowest being in the peri-urban soils. Bulk density, kind of the reverse of that, and bulk density is related to soil compaction. It's the dry weight of soil in a known volume. So in terms of soil health, lower bulk density is generally considered better. So higher bulk density in the peri-urban soils, lowest bulk density in the container soils. Calcium was highest in the urban container and urban in-ground, lowest in peri-urban. Magnesium, similar to that, as well as zinc. And then lead was significant and the highest in the urban in-ground. You can see there was one, so this is the new EPA level. I had to remake this picture last night because I made this a few months ago when the EPA level was still at 400, but it didn't really change the conclusions much because there was still just one site with lead above the old or the new EPA screening level of 200. I believe that California has a lower screening level of 80, so that's important to note, that there are a few sites, that would be considered potentially high. And this is the arsenic screening level, I think 37, so none of the sites were above the screening level or considered high for arsenic. Okay, elements where city was significant. Carbon stock, so this is taking both the bulk density parameter and the total carbon parameter to express carbon in kilograms per meter cubed. So the Medellin soils in general had the lowest amount of carbon. And related to that, the carbon to nitrogen ratio, was the higher in Medellin soils. And I would say related to that, because I think the reason we're seeing more carbon stock in these soils is probably the availability of compost, the availability of organic materials is probably higher, seems to be higher. in the Chicago and Seattle-Tacoma urban farm areas than Medellin. And so those materials would probably come with more nutrients as well, like nitrogen. So that would create a lower C to N ratio as opposed to the materials that are available and or not as many rich kind of materials being applied, it seems like in Medellin. And magnesium was significant for farm type, also significant for city, so higher in Chicago and Seattle, also potentially related to more organic inputs. Similar with phosphorus, probably more organic inputs in Chicago and Seattle. pH, that's interesting. So much higher in Chicago. And, I know that our climate in Seattle does tend to create more acidic soils. So that was kind of a nice tight grouping among all of the different soils in Chicago for more alkaline pH. And also interesting, sulfur much higher in Medellin than in Seattle and Chicago. So just to maybe try to explain some of what we're seeing there, organic matter and bulk density fit predictable patterns with a degree of anthropogenic influence. So if we remember back to that anthropic gradient or the anthropogenic gradient, the human impact, and sort of the design of this study would be to say, well, these container soils are obviously the most influenced by humans. And then we've got the urban in-ground and then the peri-urban. And so organic matter and bulk density kind of fit what what I would have expected in that case. The carbon to nitrogen ratio, carbon stock, phosphorus indicate, at least to me, more organic amendments being added in Seattle and Chicago. And then decomposition rates are also higher in the tropics, so that could result in more carbon being lost. I didn't make basically in terms of site selection, and that would be a great topic for discussion. I tried to find I wanted to find community gardens or commercial gardens. So I didn't sample anybody's backyard garden. I was really looking for something that was more for production for sale, or at least in a community garden sense. And I didn't do a lot of sort of survey about management practices because it would have been hard, I think, to get very good or meaningful data from that. But I did sample from vegetables only, from edible materials only. So I don't have, like, I can't say I don't have good data to say how many kilograms of, or tons of compost each site added to sort of analyze that further. And then this sulfur, I've spent a good amount of time trying to figure this out. There is a potential of, you can find maps, you can find better maps in North America than you can in South America of sulfur deposition from like historical coal burning. I'm not sure that explains what's going on in Medellin. I think it's probably more volcanic origin from the studies that I've been able to see. There are some volcanoes in the area. There's been that's part of the soil development there. And when I've read and sort of researched the sulfur in soils around there, it seems to be mostly attributed to volcanic origin. But also organic matter and phosphorus both reduce sulfur bonding. So, we had lower organic matter and lower phosphorus in those soils, and then more weathered soils also retain sulfur better. Okay, so looking at trying to explain what mineralizable carbon is taking a little bit more of a when we look at total carbon, that's all the carbon, all the organic carbon in the soil. And what mineralizable carbon does is try to look at a slice of carbon that might be more active, more readily available for microbial degradation. It's a pretty simple process in the lab. It's just looking at how much carbon dioxide is mineralized over a 24-hour period, or in this case, it was actually a 96-hour period. And so that is, going to tell, it might be related to a recent amendment application. It might be related to other farming practices. And the parameters that best explained, that significantly explained the mineralizable carbon were the total carbon, which is not surprising, the C to N ratio, the sulfur, which might be, in this case, a proxy for city, and then the bulk density. So those parameters together did a good job of explaining, the carbon, mineralizable carbon. And then I think also importantly is lead, arsenic, and nematodes were not well explained by multiple linear regression. And what that tells me is that these parameters, lead and arsenic, are probably more site specific. So there's not some like management practice or some global or general factor that is contributing to that. It's going to be much more localized. And as I mentioned in that CSA news article that I mentioned, they talk about that in one of the studies they refer to, about how even within a certain park you can find these hotspots. So I think that the take home there is that with something like lead and arsenic, it's going to be very hard to predict from other parameters. It's something that just has to be tested. And then nematodes, dear to my heart, and I've done a lot of work with soil nematodes, and they are highly influenced by management practices, especially those different indices. And that's not something that I controlled for in this particular study. So recent disturbance is going to have a huge effect on what we see in terms of nematode communities. And this is just another way of kind of looking at this. This is a correlation diagram, and things that kind of end up on the far ends on either side have a lot of other things correlated with them. So nitrogen and carbon are highly correlated, carbon stock. The things in the middle have very low correlation with other things. So this would be, in terms of correlation coefficient, this is 0 here, and then this would be 1 up here, and this would be -1 down here. So things can be negatively correlated, like bulk density and carbon. But you see like lead, arsenic are just not well correlated with other parameters. And that also explains why they're not easy to fit with the multiple linear regression. All right. In conclusion, one of the thoughts that I dove into here is, and a predecessor of mine wrote a little bit about organic matter, and he wrote a lot of, Craig Cogger wrote a lot about adding organic matter into soils in the city. And he says at one point that if research shows increasing physical benefits with increasing compost application rates up to the maximum rates studied, in that case, in his case, it was about 1/3 by volume of the amended soils, is there an upper limit on compost application to degraded soils? So they looked at all the way up to 1/3, and they just keep seeing better and better and better production, or better and better soil quality with the more organic matter. So, what is the upper limit in terms of adding, like, can we grow essentially in 100% compost? And the things to be aware of in that situation would be the salt content of the soil compost mix. So some composts are going to be higher in salts. And if we increase that level too high, that can start to have negative effects. And then the other potentially negative effect is the water dynamics. So when we have a lot of organic matter, a lot of compost in the soil, that can hold on to water, create anaerobic conditions. But I think if soils are well drained, if salts aren't a problem, then you can have very productive soils with a lot of organic matter. And that, I think, speaks to one of the real benefits of urban agriculture, being close to amendments, being close to, basically closing these waste cycles, and in a responsible way. There's this term organoponics, which seems to be mostly linked to cultivation in Cuba, where it basically is just like this highly intensive agriculture with a lot of investment, a lot of amendment into small areas. And the result is, kind of like what I found, essentially from a soil science perspective, we'd say off the charts organic matters, but still people are growing successfully in these soils. So I think that's an interesting area for further exploration. And just some other reflections. This was a great opportunity to have what I call conversations with the soil. I dug a lot of soil pits. So I dug 3 soil pits at each of 27 sites, although I guess with the container soils, they were a little bit easier. They're only 15 centimeters deep. But for the other sites, I did go down to 60 centimeters. And it's really fascinating to be able to see those soil horizons all over the world. And then, of course, with the farmers around at these different sites, people that gave their time and allowed me to sample their soils. And then just being on sabbatical, having that flexibility and freedom to explore this new area, to be able to land in Chicago. I did have nine weeks in Medellin to find my sites and do all the sampling, and that was difficult. But to be able to land in Chicago and sort of get all this work done in about a 2-week period, just by being flexible and having time, and not something that what my days normally look like. And I would like to express my extreme thanks to Universidad de Antioquia agriculture faculty, Drs. Marisol Medina Sierra and Silvio Ayala Lopera. And then also in Medellin, there's a nonprofit called Fundación Salvatierra, and David Villegas there was instrumental in helping me find farm sites. In Chicago, this is Dr. James Montgomery. He is at DePaul University and really planted the seed for this sabbatical for me. About 7 years ago, he gave a talk to the Crop and Soil Sciences Department at Washington State University. He's got his PhD there and now teaches soil science, environmental science at DePaul University. And he's done some great work in urban agriculture and urban soils in Chicago. So I worked with him in the Chicago area, and then many different farmers around Seattle, Tacoma, and of course, the Western Center for Metropolitan Extension and Research for supporting the fellowship. And if you are interested in more, here are some great resources. These are our books that are available: Anthropogenic Soils, Urban Soils, and Sowing Seeds in the City. The anthropogenic soils I do highly recommend from sort of that pedological perspective and describing soils. And hopefully we have some time for a few questions.
Yes, that was great. Thank you very much, Doug. We have a couple of questions in the Q&A. So first one was, what soil extraction method did you use for the chemical analysis?
That is a great question. I will have to get back to you on that because I sent it to a lab and I don't have that right in front of me. I did it at a soil testing lab. If you send me an email, I would be happy to find that information. I could probably get it, but it would take, I look for it right this second.
Okay.
I don't see the Q&A. I see the chat. Is there a Q&A as well?
There is a Q&A if you, I don't know if you need to expand your Zoom far enough out so it provides it, or maybe it's just provided to me.
That's okay. Yeah, you can, there it is.
But,
Q&A. Got it.
yeah.
I don't see any in there though.
It should be in the open. Let's see, it's.
Well, are there more in there? I do see some in
Yes. Yeah, there are a couple. So there's the next one in the Q&A, and this is going to test my chemistry, but carbon nitrogen ratio analysis affected by calcium carbonate, CO3 presence?
No, because it's organic carbon. so there's yeah, the calcium carbonate is inorganic carbon, so we're just talking about organic carbon. So organic, if there was any inorganic carbon, which I don't think there was any inorganic carbon in any of these soils, it would be removed before the total carbon. So it's total organic carbon to total nitrogen.
Okay. And the last one I have in here in the Q&A is, based on what you learned from your study, what would be your major recommendations, e.g. the top three, to a beginning urban vegetable farmer and an existing urban farmer, for example, in Seattle, so that they can farm sustainability?
So major recommendations to
Beginning and existing urban farmers around sustainability. I can throw it.
I can see it. Yeah, that is
Okay.
I mean, that has so many different elements to it. So sustainability, we often look at the, the social, the environmental, and the economic. So all three of those are going to be important. I think the social element of urban agriculture cannot be overestimated. So it provides such great opportunity for engaging community members, engaging youth in science, in agriculture. So I think, the social sustainability, I wish I had kind of a social scientist to come with me on this study, or just to look at that element, because it wasn't something I observed and I could see, but I didn't, it wasn't the focus of this study, like how are these farms impacting their communities, but clearly they are. And there's amazing examples in all three urban areas that I went to of that component. Economically, there's definitely a good deal of in Medellin, for example. One farm I'm thinking of, there's sort of 5 families involved in that, and it's definitely an important food source for them. They sell some as well, but there's a lot of just kind of local consumption of food. There was a kitchen garden in Chicago that is, unfortunately, I think it has since closed down, but it was a really cool model of a farm on a rooftop where the produce went to the restaurant, but it also created like this amazing rooftop deck, where you're just like in the farm. So I think that's that's sort of getting to the economic sustainability, like figuring out how can this farm make some money, support itself. And that was a cool idea there. For, again, I do think testing lead and arsenic are fairly easy to test. The the hydrocarbons, some of the other chemical compounds I did not test. They're more expensive to evaluate. So that would be a little more tricky, but I think, definitely doing some testing for contaminants, especially for an urban in-ground soil. That's I'm an urban gardener, and that's how I farm. I definitely do the urban in-ground model, though since my sabbatical, I'm experimenting a little more with container production. And I had my soil tested. There are some rules of thumb that seem to be true around like that local hotspot idea, right? So especially with older houses, anywhere where there was lead paint used, the soil near the house is higher in lead. On busy streets, you might have some lead, but like I farm basically right on the street, and it's not an incredibly busy street, and lead levels aren't high there, but I'm sure they're higher right next to our house. So yeah, those are some things to to take into account. But I would say like one of the findings from this study is it's, it's very hard to predict. So the local testing I think is important, especially for the urban in-ground. And yeah, utilizing organic amendments that are available is always a good idea. And I think that's a niche for urban production. I see one in
Great.
the,
Oh, is there one in the chat?
there are a few in the chat. Can you share the reference site for the new soil compost? Not sure I get that one, Jody, if maybe you could ask that again. I'm an urban ag production extension educator in Chicagoland. Done some observational soil testing work with our growers over the past 3 growing seasons. Oh wait, that was to me directly. Sorry, I'll follow up with that. I guess there aren't any except for this one about the reference site for the new soil compost. Sorry, I don't understand them.
Was that the journal article?
Oh yeah, I didn't have a link for that, but I think if you just Google CSA News, that's the crop soil agronomy newsletter. And I hope it's free. I think it is free and available, but I can't be.
Okay, I think Jody might email you directly to clarify what she's
That was the
asking.
new hydroponic option. Maybe she's referring to this one. Hopefully with that title, you can find it. Yeah, I was just this concept of organoponics. And again, the definition of organoponics seems to be a little bit meandering, but it did come around. It seems like it came out of this just concept of really highly intensive agriculture using a lot of amendments. Definitely linked to sort of the Cuban model. But there are these articles where they show, using like these articles looked at compost as an alternative to hydroponics and compared them.
Okay, and I think Zachary has a question. Zachary, can you unmute yourself or do you need me to do that?
No, I can. Can you hear me?
Yes.
Yes.
Great. Thanks, Doug, for the great presentation. So I just wanted to get your thoughts on 2 things. One is you mentioned this idea of upper limit for compost usage. A lot of our work at U of I Extension here in Chicago is focused on this very question. And we're finding that the phosphorus loading with these kind of really high upper limits up to 100% is kind of through the roof in some cases. That's I asked a question about your extraction method because we were finding 10 to 15 times what like the normal Bray P1 level should be in these systems. And there's some work out of Minnesota, Dr. Gaston Small, and some work from Nick Kalinsky at University of Minnesota looking at phosphorus budgets in these urban watersheds and these kind of high upper limits of compost usage potentially being an unrealized problem with that. I know phosphorus movement in rural agro ecosystems isn't as big of an issue unless they're tied to drain tiles. But in these kind of, cap and fill systems with these kind of, layers, there's just a lot of concern about potential phosphorus runoff. I think in Gaston's study, he looked at this model where like 30% of this transect that they studied, 30% of the phosphorus budget was coming from these urban farm systems that are loading high amounts of compost. So just wanted to get your thoughts on that, because that's some of that sort of messaging and sort of rate recommendations. That's a lot of the work we're focusing on right now.
That's really interesting. Yeah. So that you just kind of reiterate something that I heard, and I'm not 100%. Like when I hear it, I don't really believe it, but that in Chicago, people are using essentially 100% compost, right? In some of those farms, yeah.
In some cases, yes.
Yeah. I mean, it certainly looks like that. I mean, I think the highest organic matter I found was in Seattle, though, at like 27%. So even out of the Chicago areas, I mean, they were definitely high 20s. And yeah, I know there's inorganic matter that comes along with compost as well. But no, you bring up a very excellent point, and I definitely look into that, the research of the. I mean, it seems like maybe with a container operation that could be controlled, but with the cap and fill, that's what I was saying earlier, how they're sort of this hybrid between container and in ground, and I could see how with that impermeable layer, it's almost like a tile effect, right?
Yeah, and I've been looking in to figure out how to monitor this, because we obviously, all states and all extended services do a lot of that sort of tile monitoring, nutrient reduction, loss strategy monitoring. But in the urban areas, like that footprint from like where that runoff, kind of that lateral runoff begins and where the storm drains meet is in some cases like inches to feet. So like that, it's, I don't think in the current state, it's this sort of earth shattering, like urban farms are causing the hypoxic dead zone issue in the Gulf of Mexico, but it certainly is. If this is going to be scaled up and compost usage is going to be a big part of it, I think there's a lot of more education and research that needs to focus on this. And it looks like in the literature, like Dr. Gaston Small and a few others are starting to like kind of dial into this a little bit. So it's kind of interesting. But our observational work, I'll share it with you offline later, we can chat, but our average organic matter levels for Chicago were meeting pretty close to what you were showing, and pH, very, very similar cluster around that kind of 7.5 alkaline pH, and organic matter levels just kind of through the roof in that kind of 20, 25 range.
Yeah, excellent. Thank you for sharing that. No, I'll definitely incorporate that.
Yeah,
Oh,
maybe
the other question I had is I've heard this term in the literature too, technosol. And I wonder if you could, because you actually gave me a lot of new sort of terms that I hadn't heard before.
Yeah.
And I've seen this term technosol. Can you talk a little bit about that, or do you have any differentiation between that and neogenic?
Yeah, so I had it in a note on this slide. It says often urbic technosols formed on rubble and refuse of human settlements. So that is what a so urban, a lot of these metagenic soils, or sorry, a lot of these neogenic soils would be called technosols if they're formed on rubble and refuse of human settlement.
Perfect. Thanks for the clarification.
Yeah, that's like I tried to remove some jargon, but that Howard book with anthropogenic soils is fantastic, and I honestly, like, I wish I had kind of absorbed more of it before I did the site selection. This is like one of the other things, kind of, where is that? Kind of. So in hindsight, right? So site selection, I think, was a bit of a kind of winging it, maybe is a good way to describe it for this study. And I think that, and I've gone back and looked at this, and I think that the urban in-ground does not necessarily mean neogenic. I'm just kind of doing some like self-reflection here, but I would, in going forward, I think that that terminology, for example, that you picked up on, I think that's really, really important as we go forward in this work. And in hindsight, if I would have selected like based more on this group than this group, but this is easier to see, from like without digging in the soil, it's easier to say, okay, this is a peri-urban, this is urban. It's in an urban environment and it's in the ground, but that doesn't mean it's neogenic. Like kind of what you were just pointing out with the technosol. Like just because it's in a city and in the ground doesn't mean it's on disturbed rubble. And so I know I had at least one site which would be classified in my study as urban in-ground. That's not like it was just a natural soil, right? And just the way that housing development worked, like it wasn't really ever disturbed, I don't think. And so it's not gonna have like those artifacts of like a truly sort of technosol would. So great question.
And then maybe quickly, the last question I see is in the chat about person oversees several urban youth groups in Milwaukee on extension lands and is wondering what's the most efficient and economical way to test soils and keep a pulse on improvements.
Hey, it's hard to beat a soil testing lab. And I would just find a soil testing lab that you're happy with and work with them. You know, things like pH, phosphorus, the nutrient components. Those are really the most important thing. And then of course, the heavy metals. So in terms of heavy metals, where's that article? In this article, they do talk about some new very quick methods that can be done kind of on the site with like a gun essentially that shoots a spectrum at the soil and then gives you a lead. So that you can read about in this study, but I say I recommend finding a good soil testing lab. It's really no different than agriculture in another setting. It is a little bit harder to interpret, I think, and I don't know that we have as soil scientists, right, a lot of experience with soils with organic matters of 20-25%. So I think we're all kind of learning like what is different about that versus a more mineral traditional soil. But I would assume that the fertility analyses done would be similar. So, you know, you're probably gonna like if there is a lot of compost being added, you may find that you know, a lot of the nutrient requirements are being met, if not exceeded, in the example of phosphorus.
Okay, great. Well, thank you very much. Thanks for those of you. I know we've ran a fair bit past time, but that's okay as a good discussion. Thank you, Doug. And I think you all had his contact information if you had further questions, but really appreciate it, Doug. Thanks a lot.
Thank you.
Yep. Bye, everyone.